In this exercise, we're going to take a look at the more complex contrast formulas. And you can see that I've gone ahead and scrolled down inside this file, blendmodemath.psd. And I've also assigned these formulas a slightly different color scheme, just so you can tell them apart. Almost all of the contrast modes involve an if-then proposition. Notice if the pixel is lighter than 50% gray, then Photoshop does one thing. If it's darker than 50% gray, it does something else. So in the case of overlay, which is your when in doubt contrast mode, Photoshop is concerned with the luminance of the background pixel. So if the background pixel is light, that is, its standardized value is more than 0.5, then it goes ahead and applies a kind of modified screen formula. Notice we have the A plus B minus A times B, just as we do up here for screen. But we also have this 2x multiplier, which goes ahead and brightens it, and then Photoshop turns around and sinks the brightness by subtracting 1. The reason it does this is because it needs to fade that screen effect. Bear in mind that when you apply overlay or any of the other contrast modes, you need to somehow reconcile the fact that you're brightening the brightest pixels and you're darkening the darkest pixels. And you don't want there to be this sudden transition in between, which is what you'd get if you just used the standard screen formula. So, in order to make sure that the midtones drop away, so the brightest colors are still going to be very bright, the darkest colors will still be very dark, but anything that's a midtone on the active layer is going to slowly fade away, and Photoshop accomplishes that with that 2x multiplier and that minus 1 at the end. Similarly, if the background pixel is dark, that is less than or equal to 0.5, then Photoshop goes ahead and multiplies those pixels and adds the 2x multiplier as well in order to create the fade. So think of it this way. Imagine that both A and B are 0, so they're black. Well, even if you multiply them times 2, they're still black. So black is always nice and black. It's those colors as they slowly become brighter and brighter, that 2x multiplier ensures that they brighten up so that the midtones, as I was saying, drop away, so we get a fading multiply effect. Now, you might suspect, well, gosh, doesn't it go too far at some point with the 2x multiplier? That seems like a lot. Imagine that A is 0.5, so it's right there at 50% gray, which turns invisible after all. Well, 2 times 0.5 gives you 1, so it's just 1 times the luminance level of the background pixel, which is why you see the background pixel. You do not see any of the foreground pixel. So that's how it works. For soft light, notice that I have if A ... Well, what that's telling us is that we're concerned about the brightness of the active pixel, not the background pixels, as in the case of the overlay mode. In fact, all of the other contrast modes are concerned with the brightness of that active pixel. However, I don't know what the precise formula is. I found about 10 formulas online, I should tell you. And Adobe, by the way, does not share this information. That's why I had to go out there and try to seek it from other folks. But unfortunately, I conducted tests on every single formula I found, and they just did not work. So it's some kind of complicated formula. It seems to be the most complicated of the bunch. But what we know is that soft light is a weak commuted overlay. And by commuted, I mean we're concerned about the brightness of the active layer pixel and not the background pixel. I'll explain more about that in a moment. By weak, I mean that whereas overlay treats white and black as absolute brighteners and darkeners, the soft light mode does not. So anything that's white or black inside the active layer will be translucent to some extent. I do want to emphasize something. No matter what formula actually exists for soft light, it is not merely a reduced opacity version of overlay. That's just not true. It is an absolutely unique but more subtle effect. All right, next we've got hard light. Notice that hard light uses exactly the same equations as overlay. So there's our brightening equation, that same variation on screen. There's the darkening equation, that same variation on multiply. The only difference is that we're concerned with the luminance of the active layer, not the layers behind it. And that means that hard light is identical to overlay were you to reverse the layer order. You would get exactly the same result. And that is the definition of a commuted blend mode, by the way. So overlay and hard light are commuted versions of each other, just in case you ever hear that bandied about. All right, next we have vivid light. Vivid light is again concerned with the luminance level of the active pixel, that is the pixel on the active layer. And if that pixel is brighter, then we end up applying a variation on the color dodge effect. So you may recall that color dodge inverts the luminance levels on the active layer and then divides them by the background layer. In the case of vivid light, we take 2 minus 2a. So it's still an inversion, but it's 2 times the inversion. And then we divide that by the background layer. And the whole reason we have that 2x multiplier, once again, is so we can get a fading version of the color dodge effect. So we still have that over-the-top clipping, hence the warning. However, the lightening effect and the darkening effect come together and fade seamlessly into each other toward the midtones, which, as always, turn transparent. So that's something to bear in mind about all the contrast modes. 50% gray on the active layer is always transparent. Next, if that active pixel is darker, why then we go ahead and take that color burn equation and we double the brightness of the pixel on the active layer, and that creates a fading color burn effect. Linear light is interesting in that it's the only contrast mode that does not require an if-then proposition. What we're doing is effectively merging the two equations. So you may recall linear dodge is a plus b, and then linear burn is a plus b minus 1, and then we take linear burn and we double the luminance of the pixels on the active layer, and that works whether we're working with bright pixels or dark pixels. So it's an automatic fusion of linear dodge and linear burn into one equation, and of course it results in clipping. To make short work of things here, pin light is a fusion of the lighten and darken modes. So we're trying to find the max value if the pixels are bright, but instead of a, it's 2 times a minus 1. So it's a kind of inversion, but not quite. And then if the pixel is dark, we're finding the minimum of 2a or b. And the whole reason we have the multipliers in there is to ensure that the midtones drop away. So one way it's lighten with modified midtones, and the other way it's darken with modified midtones. And then finally we have hard mix, which is a derivative. What do I mean by that? Well, Photoshop takes the result of the vivid light mode, and then it looks at each one of the independent color channels, and it changes all the pixels in those channels to either black or white. And when those channels merge together, so we have a red channel with just black and white pixels, we've got a green channel with just black and white pixels, and we have a blue channel with just black and white pixels, and that ends up giving us a total of 8 colors in the full color composite image. And that, my friends, is what's going on with the contrast modes inside Photoshop. In the next exercise, we'll walk through the inversion, cancellation, and component modes.